Hello everyone. Hello everyone. So today Hello everyone. So today we are dealing with week 6 content and the questions associated with week 6. So basically it covered some sort of random processes last in the last lecture we covered, and in this lecture we will be seeing the MATLAB simulations as well. So yeah, I'm starting today's class. So here, as we know, in case of previous simulation, this was the simulation of the discrete time equivalent system. I uses toolbox random symbols. So if we have the digital match filter, the vector received contains the noisy output sample from the analog front end. And in real systems, these samples would be processed by digital hardware to recover the transmitted bits. Such digital hardware may be ISIC, FPG, or DSP chip. The first function performed there is actually digital match filtering. So that's what we have to also see how digital match filtering is happening, because the filter must match the frequency of the input. Okay, and this is a discrete time implementation of the mass filter discussed before. The mass filter is the best possible processor for enhancing the signal to noise ratio of the received signal. Okay, so in our simulator, which I am focusing on, the vector received is passed through a discrete mass filter and downsampled to the symbol rate. The impulse response of the mass filter is actually the complex conjugate complex of the time reverse, discrete time channel response. Okay, so we have input. Okay, and first of all, we will do conjugate complex, that is H star minus n, and we will downsample to the FST, and then we will pass to a slicer. So MATLAB code for digital mass filter, we can see here is, first of all, this will be the function MF out is equals to DMF, that is received, pulse, and FST are the inputs. So the body of the function is actually direct implementation of the structure in the block code above. So that can be directly temp is equals to time reverse pulse, because we wanted a time reverse pulse as per this equation, okay? This block diagram. So temp is equals to received conjugate flipper pulse, okay? Then again we have to downsample. So downsample we have to with the length of pulse, okay? Then we have to downsample with the length of pulse at the frequency at the interval of FST to the n. So this is the interval. I hope you all agree. So if you see digital match filter input and output, so you can see very perfectly how the noise is removed on how smoothen the signals it came out. Okay, so here we can see we have the perfect signal out after the DMF output. Okay, and if we see the IQ scatter plot of the EMF input and output, so you can see we have separately done the separation of a real part as well as imaginary part. Okay, you can see this is imaginary part, input and output. The noise content is has been gradually reduced. Okay, so now, as we know, we have to downsample it. Then the final operation is to be performed is a slicer. So what slicer does? The final operation to be performed by the receiver is deciding which symbol was transmitted. This function is performed by the slicer. The operation of the slicer is best understood in terms of IQ scatter plot on the previous slide. The red circles in the point indicate the noise-free signal locations for each of the possibly transmitted signal. The red circle, as you can see, that was a possible transmitted signal, right? Here you can see this is a red symbol. These are the red symbols. The red circle in the plot indicate the noise-free signal locations for each of the possibly transmitted signals. For each output from the match filter, the slice determines the nearest noise-free signal location. Okay, anyway, we want to know like what signal was transmitted, and that's what we are doing. Okay, the some adjustments to the above processes are needed when symbols are not equally likely. Then we have to multiply with some probability. Then we will get how can we have that signal location. Okay. Now let's see MATLAB function for the simple slicer. Okay. Now what it is giving? First of all, it is giving decisions. Okay. And also it is giving mean square error. So these are the output. Okay. And the name of the function is simple slicer. And what is the output? What is it? What will be the inputs? So it will have MF out, alphabet, and scale. These are the inputs. Okay. So we have to loop over symbols to find the symbol closest to MF output. So noise-free signal location. First of all, we will scale, because if we provide the amplitude or scale, then we will have some sort of noise free signal that is multiplied by alphabet at the index of kk. So this is actually array. Okay, so equal distance between each observation and the constellation point is actually the difference between we have to take apps means positive like this, then MF out minus a noise free signal. Okay, so noise free signal first calculated, then it will be it is calculated for uh, this MF out with respect to noise free signal. Then we have to find the location. So again, the location will be like it should be changed. This find the locations for which the distance is smaller than the previous best. Okay, to change the DEC is equals to distance less than minimum distance. So first of all, distance. So what does this mean? This is actually if it is array, so it will find only that locations, it will give only that distance which is less than minimum distance. Okay, if it is array 1, 2, 3, 4, and minimum distance is supposed 2, so what values it will give as a change deck? 1 is less than 2? Yes. 2 is less than 2? No. So only 1 it will give. Okay, store the new minimum distance and update the decision. So again, the min distance will be changed by this particular value. If it is valuing this one, so it equals to distance change deck. Okay, so decisions is equals to decisions at change deck is equals to alphabet kk. So again, the alphabet is nothing but a one value, okay? And then we have one vector. So kk is going to from one loop to another to the length of alphabet. At every point, we are first calculating noise-free signal. Then we are calculating gradient distance. Then we are finding the locations for which the distance is smaller than the best. Okay, so this is actually locations. Once we find the locations, we'll store the minimum distance and update the decisions. So minimum distance again that will be that will be stored or updated for the change distance, and the distance for the change deck will be again the alphabet kk. So in this way,
Sorry, ma'am, to disturb. I have one doubt. So,
yeah.
why are we using Euclidean distance here? Why not Manhattan distance?
Yeah, so basically, the slicer is the basic uh, this is rule decision making. In communication system, by default, we use equivalent distance. But yeah, you can also use different distance, but equivalent distance is considered the main function as per the standards.
But as per the formula, as I can see here, there is a absolute MF out minus noise free signal.
Yeah.
So, uh, is this not the formula for Manhattan distance?
What is the difference between Manhattan distance and equivalent distance?
So Manhattan distance is a mode of x2 minus x1.
And equivalent distance is actually square of x2 minus x1, right? Root over.
Yeah, square root.
Huh. So if you talk in terms of bits and one minus one, so equivalent distance and your whatever your distance you're telling, that is same.
Uh, okay, you can go ahead.
Okay, thank you so much, Raja, for asking questions. So yeah. Now, the entire system. The addition of the functions for digital match filter completes the simulator for the communication system. As we have seen in the previous class, what are the block diagrams? We saw what is source encoded, then channel encoded, then channel, then modulator, finally channel, and then finally at the channel the noise will be added. And after channel, you are doing this match filters and all to extract what was transmitted actually. Okay, the functionality of the simulator is encapsulated in a function with a signature. Okay, so now this MC simple is comes into the picture. The function simulates the transmission of a sequence of symbols and determines how many symbol errors occurred. Now we have determined like what symbol was transmitted. Now we have to check uh, what how in how many symbols this actually errors occurred. So that's how we have to determine how good the system is. So the operation of the simulator is controlled via the parameters passed in the input structure. Okay, now we will see uh, some of the real time uh, MATLAB simulation. I'll share my screen so so that you will understand. Raja, can you please tell whether my screen is visible or not?
Not visible.
Not visible. Is it visible?
Yeah, yeah, now it is visible.
So we covered everything. Simulate a basic digital communications link in the previous class, also pulse shaping filter. Then we were talking about what was multipath channels, and that time the class was over. So again, I'm starting from that point only. Give me a second. So this wireless communication on-ramp is a guided course, and I'm relating with the subject which is taught in the NPTEL, so that you will get the exposure to practical simulations part also. Because the name of course itself is a simulation of communication system using MATLAB. So yeah. So yeah, we talked about QAM modulator, transmit filter, and QAM demodulator and receive filter. We saw all these things in the last class. But in the channel we simulated only AWGN, okay? But in reality, you will also have multipath components. So how we will do that multipath component, will start today here. Okay. So in this activity, we will add a multipath channel to your simulation. The multipath channel precedes the AWGN because the multipath is encountered in the air. What is multipath? So once a signal is transmitted, so it is not directly transmitted to you or the desired user. So it is getting reflected to various buildings. It is getting reflected to various obstacles. So in this way, you are having so much path. So that is like a multipath. And in order to do the channel modeling, you have to take care of these multipath component in the channel. Now, there is a huge area of research where people do channel modeling for 5G or 6G, where people are also using ARML to estimate some of the components um, for the best channel modeling, because predictive channel modeling is always required. Class. uh, so for simplicity, you will simulate a static channel. However, in scenarios where transmitter, receiver, and reflectors are moving, the channel impulse response will also be time varying. Now we will see non-time varying as of now, but that's why the signals and system comes into the picture. So the COM modulator we already saw, the transmit filter we already saw. Now we will see the multipath AWT. Now you can represent the multipath channel as a finite impulse response filter. In MATLAB, the FIR filter can be defined by the vector of coefficients. So now let's see, we have B is equals to B0, B1 to Bn. For a multi-path channel, you can think of a non-zero coefficients as representing one path and each vector element after the first as a delay of one sample. So suppose this is MP, where you have you have you can think of a non-zero coefficient representing one path and each vector element as a delay of one sample. So after which one element will be as acting as a delay. Okay. So suppose this P1 0 0 is acting delay, then P2 then 0 0 delay, then P3. So to P1 P2 P3 are actually pulse, or as we know, all the naturally occurring signals are analog signals, and then they are sampled, discretized, and encoded. Then they are converted to a digital one. Okay. Then finally, digital signals are sent over the pulses. So that's why P1, this one is written, and these are the bits. And the bits are sent over the pulses. Now, since your signals are the column vectors, it's good practice to be consistent and make coefficient vectors also a column vector. So let's have this as a coefficient vector. Transpose a row vector to this column vector. Okay. Now we have to create a column vector named MP channel, multipath channel, with 17 elements. Set the values as this one. Now, as we know, in the previous class, we checked number of bits we have taken 20,000. And why 20,000 should be the multiplication of comm? Because the order of modulation is 16. And log 216 is what? 4. So, 4 symbols in one form. So it will be COM16 COM modulation. And now bits, that's what bits per symbol is. Mod order is equals to 2 power bits per symbol. So bits per symbol is actually log to mod order, as we already saw in the last class. And transmit filter, we know that transmit and receive filter both are the raised cosine pulse. The raised cosine pulse has an advantage as their Fourier transform has a limited bandwidth. Okay, so transmit filter was raised cosine pulse as well as receive filter was also raised cosine pulse, because they should be synchronized the same frequency. Where we have these properties, the shape is square root, roll off factor is 0.2, filters span in is 10, and decimation factor is 8. So you can see in the receive filter you have the decimation factor or down samplings, whereas in a transmit filter you have the up sampling. So you have upsamplings, output samples per sample. This is a upsampling. The roll-off factor was the same, and filter spans in symbol is 10, and gain we have considered as a 1. So in both the cases, we consider gain as 1, but we can consider different gains as well. So source bit we have generated randi. Let's first see randi 0 to 1, and the size is number of bits cross 1. So we'll first see this one, because I don't want whether you know the previous class or not. Now, after generation of source bit, we did the modulation. Okay, we did the modulation. After that, we had this raised cosine pulse. Okay, this is semicolon. So yeah, 20,000 cross one, and this should be the multiplication of 4. Okay, now what was written here? MP share is equals to set the first 9 and 17. So let's 0.8 0 0 0. So in MATLAB, you can also you can use comma or you can use space. So next value is ninth. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so MATLAB starts with 1.5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Next value is 17, 9, 10, 11, 12, 13, 14, 15, 16. Now 17 is 0.34. Now this is a MP chain, okay? But we have to create as transport because this is all we are dealing with a column vector. Here also we are dealing with a column vector. There's a reason like why we are dealing with a column vector. Let's first submit only. Okay, so it's correct only. Next task. Now you can visualize the impulse response of a multi-path channel as a stem plot. So let's see, visualize. Okay, so we can see where we are having the values. Now to apply the FIR filter, this is other FIR filter impulse responses. Okay. To apply the FIR filter to a signal, you have to use the filter function. The first input is the impulse response or the numerator of the numerator coefficients of the filter. The second input is a denominator coefficients for an FIR filter. This is always one. Okay. So talking about filter in the MATLAB function. We have first input as the this one is the impulse response, then denominator second input is the denominator coefficients for an FIR filter is always one. So I would like to tell you what is the difference between FIR and IIR. So in FIR filter, finite impulse response, and whereas in IIR you have infinite impulse response. So in cases of wireless communication, we often use FIR filter for channel modeling. But when we have the infinite number of coefficients and then we have to loop it, so then in that case we use IIR. But FIR filter we basically use because it is most kind of stable filters, so that's why we are using FIR filter. When we have loops, like we have the feedback, and again we have to model using the jet transport, that type of filter is IIR. So in communication system, we always use FIR filter. Now let's see, take out to the transmit. Filter is by default MP share, and FIR is 1 because denominator is always 1 in case of FIR, whereas in case of IR, you will have the denominator as well. Now, transmitted signal, transmitted signal was transmit, build, out. And let's keep at this. Let's first see. Okay, this is it. Now let's see first step. I want to see what was the input, impulse response, stem, uh, transmit.
Excuse me, ma'am. Can you print out the uh, transits filled out before applying the filter?
Yeah, I can plot. So yes, transmit filled out was that was the input signal, and after channel applying to the impulse response, this is the output signal. Now I want to see as from perspective of plot. So stem, stem. Will this work? What do you think? Because we are plotting the same uh, figure. So I think We have to open figure,
I
let's
think
say
only
one.
last figure will plot.
Hold on. Transmit filter out. Yes. Yeah, I think. So receive filter output showing this one. Mm, I can have different color RB. So basically, I want to see both of them. So yeah, so previous class we saw the bit error rate. So I think that only it is printing. Bit error rate, number of bit errors is equals to 4775 and bit error rate is 0.2392. And so MP chain out, the channel out is this one. And these are the two plots, red and blue. So this only we want. By default, it is printing that one, receive filter output, and from the previous class that we had. So that's why it is printing because we printed this filter out. So it is by default printing that one. Maybe some internal thing is there. So yeah, after filter out, the blue color is this one. So you can see chopped. I want to see this one. So zero point 0.6 is the maximum value in case of transmit filter out. That is red color. Whereas the zero point 0.5 or something like that, it is a maximum value for the multi-part channel out. Okay, that's why it is chopping. Basically, the filter work is chopping only. So wherever it is required is chopping, you can see here from the red color and from the blue color. Task 3 was that one only. So I think we completed this one. And if you want to see some further topic, once you have defined MP channel out in the script, the rest of the simulation executes. Okay, so that's why the rest of the simulation is executing. Okay, the BER is calculated and displayed in the output panel. As predicted, the link has been rendered almost useless by the multipart. So that's why this output was coming out. Receive filter output and number of bits in error was 4,822, whereas transmitted bit what 20,000. In that case, the BER is 0.2416. Okay, and anyway, we have to first define different parts, and in this, basically the raise, cosine, pulse, and a modulator all are defined, so you don't have to worry. To better understand the problem, look at the spectra of the transmitted signal and the channel output by uncommenting the code at the end of the script. So the transmitted signal is yellow and the received signal is blue. Okay, so I think I'll see. Okay, that's what this is by default. Transmit filter or filter span.
So will this work if we use the row vector instead of the column vector?
Why? Because input is also. Acha, you are asking like why we use
Column
column
vector.
vector.
Yeah. So if we
Okay.
use a transmitted signal, both the transmitted signal and the multi-channel coefficient as the row vector, will it work or
Yeah,
will it be?
that will also, in that case also it will work. But every time, why multiplying with the column vector is more helpful. You can see from the normal thing, like if it you are having 2, 2, 2, 2, suppose like that. Suppose row column vector is there. Okay. If you are multiplying with any matrices, so that will be simple multiplication of one value with respect to all the columns. Whereas in row multiplication, the computation required is high. So that's why we by default we take column vector. But yeah, in that case also it will work. The computation is high, so that's why we take column vector. So
Okay.
yeah, guess you can see channel 1 and channel 2. So let's say first channel 1, uh, this is spectrum analyzer. This we basically have in our labs also. So channel 1, channel 2 in the class we saw it was transmitted and received. Mm. The spectrum of the receive signal is notch in its passband, which significantly distorts the single carrier waveform. The phenomenon is called frequency selective multipath because of the level of the channel attenuation or gains depends on the frequency. Okay, yeah. So the transmitted signal is yellow. So this was a transmitted signal, and the received signal is blue. Okay, we can see the spectra of the transmitted and the received signal. Okay, now the spectrum of the received signal has notch. So that is blue has notch. Notch. This is somewhat like W shape. It is passband. So that was a passband because it actually significantly distorts a single carrier waveform. That is the phenomenon is also called frequency selective multipath because the level of the channel attenuation or gain depends on the frequency. So at that frequency, actually it is a carrier wave. So whenever we have the middle, so as we can see that amplitude modulation also, the that is it's nothing but a signal is multiplied with a carrier, that is AC cos 2 pi FCT. So the signal was shifted towards the carrier frequency where the middle frequency was FC. Okay. Similarly, it is also FC. This middle frequency is FC, but also at the same time that is notch one. So that is what we are telling. Why? Because of the channel attenuation factor. This is also called frequency selective multipath. So this is often asked in interviews like Qualcomm, where we have what is the frequency selective multipath and what type of signal it will look. So it will have the signal look property as a notch. Okay, frequency selective multipath because of the level of the channel attenuation again. So, oh yeah. Now, modern systems like LTE, like 4G and Wi-Fi 802.11p and 5G have adopted a technique to deal with this multipath. It is called orthogonal multiple division access. So that's why they asked orthogonal multiple division access very frequently, like what is it, how it works, and what is the implementation of it, and what are the blocks of orthogonal multiple access. So we will see the orthogonal frequency division multiple access in the next section in just 2 minutes. Now you may wonder, as we know, every time we have bandwidth as a shortage of bandwidth. And what is wireless communication companies are doing? They are just doing the proper efficient resource allocation. And for that, they are also adopting division multiple access, frequency division multiple access, code division multiple access. Now the fourth term is orthogonal frequency division multiple access. In that, we will have orthogonal subcarriers. So this is not a single subcarrier. So just now we have seen till now all are single subcarriers, which the single subcarriers only multiply with the input signal. Whereas in orthogonal frequency division multiplexer, we have subsequent large number of subcarriers. Now we will see what does it look like. So a multi-part channel response can be a bit long. So as we can see, this is multi-part channel response. So with a higher rate signal, the multiple signal can span the multiple symbols, as we can see. So it only spans 3 symbols of this high rate stream. So as if we have more number of zeros, so it will actually time smeared. It is smeared in the time, which also called inter-symbol interference in the frequency domain. So if we have a low rate signal, then it won't be a much problem. In that case, we don't have inter-symbol interference. Why? Because here you can see you will have the much more space. Inter-symbol interference means they are one signal is transmitting, after some time other symbol is transmitting. So they will have some common part and they will interfere at the receiver. That is inter-symbol interference. So if you have high rate impulse response, so you will have less number of interference, inter-symbol interference. But at the same time, we want high rate data. We don't want low rate data. So that's what, how can we cope up with this high rate data, but actually inter-symbol interference. So here only the OFDM helps. So OFDM is deployed for high rate data, high data rate. So HDR it is also called. So you can see it is very, very efficient technique to convert a single stream of high rate data into a parallel stream of many low rate data. So at the same time, you are transmitting various users in a parallelly. Okay. So parallelly low rate you are transmitting just to have a reduced inter-symbol interference. And later we'll see that OFDM causes zero inter-symbol interference. And that is why the property of FFT works. That is fast Fourier transform. But the question is, how is this accomplished? So let's look at the spectrum of filtered high rate COM signals. So you can see here. So the idea behind the OFDM is to divide the pass band. The pass band is where the signal is high. There only you are transmitting the signal. After filtering in this part is only take care. So to divide into smaller subbands. So each COM signal after COM modulation, it will be frequency translated to one of the these subbands that is divided. The pass band is divided into multiple subbands. Then you have the COM modulated symbols that will get one of these subbands in order to transmit. So mathematically, actually, this means that we have to just multiply the symbols with respect to e power j 2 pi nk by n. So what this frequency, this formula represents, this nothing but IFFT or IDFT. Okay, it is nothing but IDFT. So we'll see how IDFT is there, where each symbol is multiplied by a different frequency called a subcarrier. And one OFDM symbol is actually the sum of each frequency translated COM signals. So this is the sum. So this, what do you think? What is the formula? What is the translation of this? This is nothing but IDFT. So you can see we saw how it is transmitted in terms of time domain, but how it is transmitted in terms of frequency domain. So here you can see every symbols that is there are orthogonal to each other, but they are transmitted in the same frequency band. So all the users will be transmitted or will be accommodated the same resource block, but the subcarriers are orthogonal to each other. That's why they don't get interfered. So this is sync pulse. So do you know the Fourier transform of sync? is nothing but rectangular pulse. Okay, the Fourier transform of sync is rectangular pulse. That's why the symbols are transformed in terms of sync. Now you may wonder what makes OFDM wave from orthogonal. So we can zoom like this and we can see. So this is what how so the peak of one subcarrier is actually the zero crossing of other subcarrier. That's make every subcarrier as orthogonal. Also, you can check with the orthogonality properties. Integration of minus infinity to infinity f1t multiplication with f2t into dt is equals to 0. Then f1 and f2t are orthogonal to each other. Similarly, if you see one subcarrier to other subcarrier, if they are multiplied together and if they are integrated together, and if it's leading to 0, then in case that those two signals are orthogonal. Similarly, in case of OFDM, all the subcarriers are orthogonal to each other. So which means that none of the subcarriers interfere with each other. So right now, I think this is a bit complex to understand, but in 5G and 6G, even in 6G, people are only adopting OFDMA. Okay, so what we had first? We had FDM, means the resources are allocated based on frequency, where different frequency will be allocated to different users so that they will not interfere. Then TDM comes, like users will be allocated based on time sharing. Okay, time division multiplex access. Then CDMA comes, like code division multiple access, where the resource will be allocated based on different codes so that the resource blocks will not be interfering to each other. Now OFDM comes into the picture. That is the most recent form of 5G and 4G. So in OFDMA, what we have, the resources will be allocated to same frequency bands. Okay, the same frequency passband you had. Then the same frequency passband is divided into different sub bands, very small sub bands. Now the symbols, which is the modulated QAM symbols, will be uh, will be allocated to these subbands. Okay. Now this will be modulated by different carrier frequencies, and the carrier frequencies will be so much, like you will have so many numbers of carrier frequencies. In LTE, we will have 1800 subcarriers and they are orthogonal to each other. So 1800 users can be allocated to single passband. You can see that's why how we are getting high data rate. Okay, now when we have modulated symbols, they will be multiplied or they will be modulated with respect to the carrier frequency e power j 2 pi mk by n, where mk by n is the frequency of the each subcarrier, where they will differ by m. Like 15 kilohertz is the frequency of one subcarrier, then some multiplication of first subcarrier will be second frequency. So 15 into 2, so it will be 30 kilohertz. To 15 into 3, it will be 45 kilohertz. So with the multiplication of integer multiplications, these subcarriers frequency varies. Okay, once they are summed, then they are sent. Okay, to serial to parallel converter in an OFDMA. So that's what the sum process is actually IFT. Okay, in that case, the IFT reduces the processing at all. So we'll see. This is IFT. So what is the difference between IDFT and IFT? Nothing. The IFT is the fast Fourier transform of IDFT. The formula is same. When we solve in terms of trivial factor and the butterfly diagram, that is IIFT. Otherwise, it is same as IDFT. There's nothing difference between IDFT and IIFT if we talk about in terms of formula, and which can be implemented within IIFT. So that IIFT is already there in MATLAB. So the simplest possible OFDM links uses IFT in the transmitter. As we saw, this was a source base, then COM modulator. Then here we were having raise cosine pulse, transmitted raise cosine pulse. Then IFT, okay, in the transmitter, followed by FFT in the receiver. Now we will simulate it and we will see. OFDM is very little difficult to understand, I agree, but we will see only IFT and FFT and the transmitter and receiver. Then we will also see the cyclic prefix uh, addition. So in this activity, you will create a simple OFDM symbol with an IFT and an OFDM modulator and FFT as an OFDM demodulator. Okay, so you again we have power of 2 to optimize the performance, number of bits we have taken for I. Yeah, again, we have to check with the size of the FFT and IFT. That's why this particular value is taken. Okay, then modulation order again 16 com. Okay, the source bits is number of bits randomized 0 to 1. Then com modulator, after modulation, we will do com modulation. Scatter plot, again, this is like scatter plot, 16 com single. So 1, 2, 3, 4, 5, 6, like that. You have 16. Okay, 16 com symbols. Okay, again, 16 com symbols where you're having 4 bits. In one symbol, you have 4 bits. Okay. Now, the IFT function computes the inverse discrete Fourier transform of the signal. The output of the signal is same as the input of the signal. Notice that the number of bits in the simulation has changed. Okay, we will see that. It's now the power of 2. Yeah, so previously we had 20,000. That is not a power of 2, which means that the length of the COM signal is also a power of 2. So we have to also see the length of the palm signal will also be power of 2. Uh, because after modulation, the same size will be there, right? Number of bits. Now, the IFT and FFT functions are significantly faster for signals of certain lengths, including those whose length is power of 2. So, let's say we have to, after modulation, we'll do IFT, come out. So, IIT, IFFT, sorry. So, yeah, this is the after modulation. Now, once we have created a variable DM mod out, in the script, it is sent to over the noisy channel. So as we can see, that was sent to the noisy channel. In the receiver, you need to undo the IFT by processing the FFT. So the FFT function computes a discrete Fourier transform. So this is sig out FFT. So chan out again. By default, it is showing chan out because they have itself created. If it is variable, then SNR 15 and channel is AWGN. So here we didn't added the multipath component here, just the AWGN OFDM out. This is output with the SNR of 15 dB and it is measured because we are providing the value of 15. That's why it is measured. We saw this in the previous classes. That's not a problem. So again, OFDM D mod is equals to chan out. This is we are simulating as receiver part. These are some simple guided exercises that we'll see. So you can see we have the modulation out. Okay. After modulation, you are transmitting to FFT and at the end, but they will have the same size. Okay. 8192. So from where you are getting 8192? 8192. How we are getting 8192? So how it is related to 32768? Calculator. I think that will be clear soon. divided by 32768. So it is 1 by 4. Okay. So because the com is uh, 2 power 4. So 2 power 4, actually one symbol is considered 4 bits. Okay. So 4 bits it is there. So it is, if it is you divide by 4, you are getting, because after modulation only you are doing. After modulation number of bits is this one. After modulation it is divided by 4. And then after modulation you are doing FFT. Okay, you can see that modulation diagram, then you are doing FFT. So that's why the size is 3 to number of bits divided by 4. Okay. Again, they have the task 3, since the OFDM demodulator output is 16 count single, you can look at the scatter plot. Scatter. So scatter, you can look at the scatter plot. Let's see solution. Scatter plot. So it's not scatter, only scatter plot. Sometimes I do this type of mistake as so. So yeah, you can see after demodulation, you are having this much noisy signal. So this was the modulation. The symbols are transmitted over this, and this, after this, you are having up to this type of noise. So number of bits is also 149. The BER is 0.0045. With respect to input bits, number of uh, bits in error divided by number of input bits is 0.0545. That is good. It's very less. And number of bits is not number of non-zero, where it is not equals to this one. And BER, we already saw these things in previous classes. And com demod out is equals to com demod of DM modulation order, where we have to put this output type and bit and unit average as a power as unit average. Unit average power as true. So I think clear. The signal was sent over a noisy channel, so you should expect to see some noise in the cancellation as we have seen. The scripts also calculates BER. You can change the value of SNR to look at link performance. This link performs as well as noisy 16 QAM without OFDM. If you increase SNR to 20, there are no bit errors. So if you have more SNR, again, you will not have errors that we can see already. How you don't let you know how the link will do with the multipath. You will see in the next activity. Right now, we didn't simulated a multipath as a part of channel. We only had this AWGN. So we will see that multipath also with the channel effects. So the script stimulates the same OFDM link before, but now you have to modify the channel model interactively. Okay, so the script runs time you select the checkbox and move the slider. Okay, the output panel displays the PER and the scatter plot of the OFDM modulator, as we know from the previous one only. Okay, that is same. So model a multi-path channel by selecting the has multi-path checkbox. So where is the checkbox? Okay. So you can see even the symbols are collapsed to each other. You can't see any symbols separate from the each other when we consider the multipath. So that's why the SNR has a lot of effects. And if you have more SNR, let's see, 30. In fact, with 30 also we have less number of symbols we can see. But at least some symbols we can see after 30 SNR. But this is a good rangoli we can see here. But BER, let's say BER is 0.2283. Let's reduce this SNR to 3. BER is 0.30. So I think we have to increase the SNR further. But we have less number of SNR, 0.34. So yes. And if you only consider AWGN, multipath without AWGN, let's see. Okay. And let's say only AWGN. See, if we have good SNR with not multipath considered, we have, if we only consider AWGN, all the symbols are separated from each other. We can easily separate this person noisy, we can consider that. But if we have low SNR, you'll have some smeared. All the symbols are smeared. So that's good way to see. Okay. So what was the task? Okay. The multipath has again rendered the link useless. You can isolate the multipath channel by impact chaining the hash WG in this one. You can also see the frequency selective nature of the multipath channel, the scatter plot. A complex gain scales and rotates the complex constellation. And different frequencies are subject to different complex gains. The first is the frequency 1, frequency 2, and frequency C. It turns out the IFT alone doesn't address all the challenges induced by the multipath channel. To create a usable link, you will need to design a more practical OFDM symbol. So only that we have done is only adding IFT as a modulator and FFT as a demodulator. But again, we are having lots of symbols are smeared to each other when we are considering a multi-part channel as well as AWGN channel. So we have to consider some more practical consideration into the design of OFDM. So let's see that what we will design that. Now, implementing OFDM as an IFT was very simple, and the channel we consider as a multipath AWGN and COM modulated. But here we don't have a raise cosine filter. We didn't have, but again, we will have that as an internal to a COM modulator. And IFT was a transmitter, and FFT was a receiver. Simple thing, where we saw a simple passband is divided into multiple small subbands, where the symbols are transmitted over the subcarriers and they are summed together, and that summation was looking as a IFT. That's why we use IFT. Now, but as we know, we just saw that IFT doesn't help with the multipath. Symbols are still smeared to each other. But the reason you are asking why, what can be the reason? Because a channel is basically a filter. That's why we represent it with respect to impulse response. And ideally, that filter should be spectrally flat across the bandwidth of the signal. Then you can compensate for the change with a simple uh, complex linear receiver. So this is a channel, this is a transmitted signal. If it is same on the flat, we can compensate, okay? But the multi-part channel spectrum can vary across the signal frequency. That's why we were not having the simple same transmitter as the same received. And this causes frequency selective fading, where the channel responses are varying with respect to frequency, and that is causing the frequency selective fading, where different frequencies face different amounts. Now, with multi-path channel, we need an equalizer at the receiver to remove all the peaks and valleys. That is, if it is peak or valleys that is created by the channel. Now, the secret sauce that OFDM symbol is how it performs the channel equalization as well at the receiver. It's much like an audio equalizer that increases or decreases gain at different frequencies to just create the best listening experience. If you have audio equalizer, then just it creates or increase or decrease based on different frequency and creates the best listening experience. As we know that OFDM turns out the high rate signal into parallel low rate signals. In that, passband was divided into different small small bands, right? The simple band was divided into various small bands. Or so in the other ways, we can say it turns out the high rate signal into parallel low rate signals. Now each low rate signal has another bandwidth. And so it occurs in a channel whose spectrum is relatively flat because low rate signal has narrow bandwidth. And wherever the narrow bandwidth is there, the channel will almost, if the channel is considered, that is having only small or the flat channel. Or so it encounters a channel whose spectrum is relatively flat as compared to the previous one. So here in OFDM, we just have to apply the complex gain because we are not cutting off the valley and the peaks here because we are considering only low rate signals. The low rate signals are the narrow bandwidth. The narrow bandwidth, whenever it encounters a multi-path channel, it will almost pass through the flat channel. And if it is flat, maybe you will have the amplification difference, but that will only require for the amplification. That is far easy if we compare with respect to the peaks and valleys. So that means the equalizer can simply apply the complex gain. That's it. And to each subcase separately, we can apply the complex gain, which will remove the peaks and valleys. And since this equation happens in frequency domain, because this is also frequency domain, this is HK, this is RK, and implementation is easy because it's just a multiplication of SK into HK. So just you can see by just passing the multipath channel with AWGN characteristics, with AW channel with multipath characteristics, you're just multiplying with respect to the transmitted signal. You are actually equalizing also. You are equalizing it. So RK is equals to SK multiplication by HK is actually the equalization factor. And HK is the impulse response of multipath. So, so SK is simply RK divided by HK. That will create the estimates of the transmit signal. Now, this easy implementation will only hold when we have the circular convolution at the time domain. Then only S bar k is equals to rk by hk. So that is one trick is there. So that's why we are making sure the time domain the circular convolution should only exist. In that way, we have to add cyclic preface or whatever required to have this equalization easy at the receiver. So I hope you understood. First of all, we just had modulator with IFT. In that case, we saw it is not reducing the effect of multipath channel. We saw using the diagram as well. But now the equalization requires because at the end, every signals the channel is having the not flat spectra. It is having different spectra. That is due to which it is facing frequency selective fading, due to which it is also having intersymbol interference. So due to frequency selective fading, we had the peaks and valleys at the receiver. Okay, but when the OFDM input signal is divided into narrowband signals, so the each narrowband signal is only selectively having the flat channel response. So, but the flat channel response also have the amplification issues. So we can directly multiply and we can resolve this issue. But this multiplication will only work when we have the circular convolution at the transmitter or in the time domain. Okay. But the reality, the channel performs linear convolution at the in the time domain. But we have to make sure it should perform the circular convolution. So for that only we will do cyclic prefix addition. We'll see because it's just a filter. So in linear in practice it performs a linear convolution. So as we know, the channel performs by default in a linear convolution. The question arises: how do we convert the linear convolution to circular convolution? And remember that when the signal is periodic, the circular convolution and the linear convolution are same. So just we have to make sure the signal is periodic. We have to make the signal periodic. Now let's take the OFDM symbol. So this is what cyclic prefix addition. So what we have done, this blue color is the OFDM symbol. Now we have taken the last part of this OFDM symbol and prepend to the first part. Prepend to the first part. What we have done? We had just OFDM symbol, blue color. The last part was taken off and it is added to the first part. And this is all we are doing in time domain. And this particular thing is called cyclic prefix. Now you have a periodic sequence. Then you don't have any problem with the circular convolution and equalization. So now you have to make sure that the cyclic prefix should be at least as long as the channel impulse response because of the multipart fading. Why? Because the cyclic prefix will be impacted by the time spinning of the multipath channel. So it should be at least as long as HN. But since it's a duplicate information, doesn't really matter if it is corrupted also. So in the transmitter, you have the IFT output. Then we have to add the cyclic prefix to get the full OFDM symbol that should be periodic in nature. And at the other end, the receiver, the operation will be reversed, that the cyclic prefix will be discarded. At the end, we will equalize the signal at the receiver. So what we have after channel, you have to discard the cyclic prefix, then FFT, then equalize. Using that beautiful simple equation that is RK by HK. And this is why it is working. This is because it is performing circular convolution. And the output will be the COM signal that you have started with. And we can implement this in MATLAB. We'll see that. So also we can use OFDM mod that is already inbuilt is having IFT plus add cyclic prefix or discard cyclic prefix plus FFT. That's OFD mod. So you can see OFDM mod is already having cyclic prefix addition after IFT. Okay, after COM symbol, you will have IFT plus cyclic prefix addition. That is OFDM mod. And when we have discarded the cyclic prefix and FFT, that this is OFDM mod. And these functions will manage the cyclic prefix for you. Also, it will also add some guardrails so that it will not interfere the neighboring signal, and also pilot symbols to. So what is pilot symbols? There are some symbols that is sent at the transmitter, that is already known at the receiver, just to have some channel estimation properties. So we can see here, we instead of IFT, we are replacing the IFT with the OFDM modulator, where OFDM modulator is having IFT plus Adlix cyclic prefix addition. Then AWGN, we will have also have multipath effect here. That will be here before the AWGN. Then OFDM demodulator, that is already having removed cyclic prefix, then FFT, then followed by equalizer, then finally COM demodulator. I hope this is. And channel also we can perform with multipath. We'll see in the simulation. So OFD was very good concept. Charges. I'll just keep my charging. Wait a second. There are some notifications. So frequency domain equalization. In this activity, we will simulate a OFDM symbol that is already having cyclic prefix and a frequency division equalizer. As with the IFT, the OFDM modulator sends 116 COM symbol on each subcarrier. So understand this. So we had how many subcarriers? Suppose we have 1200 subcarriers in case of LT. So in one subcarrier, we will have 16 COM symbol on each subcarrier. It then adds cyclic prefix to create the OFDM symbol. Okay. The IFT is leading to the 16 COM subcarrier sending towards a through IFT, okay, which is sent over the channel. In the receiver, the OFDM demodulator removes the cyclic prefix and performs FFT. You then equalize the output in the frequency domain via division. Okay, so this is what the block diagram. When designing a practical OFDM system, the number of subcarriers, that is FFT size, is an important design parameter. So you can see what size of the FFT we have to take care. So just think about for a while. I'll just have water. What do you think? So FFT size is one of the important parameters. The simulation in this activity is designed around the number of subcarriers. The 116 COM symbol. So 116 COM symbol in the sense is one symbol is having 4 bits. Is assigned to each subcarrier, creating a single OFDM symbol. So when we have so many subcarriers, okay, so what do you think? That one symbol you are having, that will having the whole number of subcarriers. Okay, so that will create one OFDM symbol. Agree? So if you have 1200 subcarriers, so the subcarriers, 1200 subcarriers itself will create one OFDM symbol. And in one OFDM symbol, you will have in 1200 subcarrier, suppose. So in one subcarrier, there is one 16-com symbol is assigned to each subcarrier. So number of source bits to generate is calculated by multiplying the number of subcarriers by the bits of the COM symbol. So understand this. So this is what the number of source bits is number of subcarriers divided multiplied by the bits of the COM symbol. Okay. So define the number of subcarriers to 1892 and store in the name as 8192 number of carrier. So let's first take modulation order is equal to 16 bits per symbol is this one. MP change channel, this is multi-part channel, this is 0.8, then zeros 7 2. Let's see this. So here you can see here you have first 0.8, then 7 cross 1 zeros, then minus 0.5, then 7 cross 1 again zeros, then this one is. So this is like high data rate. Okay. Then calculate the number of source bits to generate. So you can, it will be multiplied by number of carriers. It's correct only. Now, after setting the number of source bits, so what was the number of source bits? First of all, now how many number of carriers you are taking? And in one carrier, you will have one COM symbol. So one COM symbol will have 4 bits. So that's why it is multiplied by bits per symbol. Okay, that's why. The number of bits is that this much is the input, and number of bits is containing this one is in one OFDM symbol. Okay. After setting the number of source bit, the script creates the source bit sequence and modulates it using 16 com. The next step is to perform OFDM modulation, including the cyclic prefix. So as we know, this OFDM mod and demod functions manage the cyclic prefix for us. So all of you have to do is specify the length of the cyclic prefix. Okay. The cyclic prefix must be as long as the impulse response of the channel. So the impulse response of the channel we had how much size we had? This was 7, 7, 14, 15, 16, 17, 17. Okay. So here the simulation, the multi-part channel impulse response is 17. So use a value slightly larger than that for the cyclic prefix length. So let's have some cyclic prefix length as 32. So at least it should be as the multi-path channel size. So we have to create source bits. Course runs source bits is run by com mod. After source bits, it is com modulation is happening. 32. So next task is use that OFD mod to perform the OFDM modulation. Specify the number of subcarriers and cyclic prefix length. Sig out. So number of subcarriers, that is com mod is the number of subcarriers, CP length also. So let's this OFDM out is OFDM mod. What was the first input? That com out. Com mod out the carrier we provided cyclic prefix length. Let's first see this one. So number of subcarriers, bits per symbol 14. These are the symbols that is already number of bits is this one. Cyclic prefix length is 32. So next task is next the OFDM modulated signal is sent over the channel. So the sig out is OFDM mod sig number of carriers CP length. And the receiver perform the OFDM demod. So that after this again the set is sent to a channel that is filter MP channel 1 OFDM out and channel out is AWGN MP channel out that is multipath and SNR that is measured. Then we are only doing this one. Is OFDM demod. OFDM demod. What will the function of OFDM demod? It will first remove the cyclic prefix and do the FFT. Okay. And as we know, the channel out should be the input here. Chan out carrier CP length. CP length is same as 32. Cyclic 3. So where I have done wrong, chan out, number care, cyclic brief. Let's see the solution. So they have done. So it's a create a scatter plot actually. So I haven't done that. Scatter. Let's see this. So yeah, let's see like this. This is a WebDM demod. The next step is to equalize because before equalization you are not removing the effect of multipath channel, right? So next step is to equalize using the easy equalization equation that is receive divided by H bar. So R is the OFDM demodulator output and H is the estimated channel frequency response and S is the equalized 16 com signal. So in this course, you will use a multipath channel impulse response H bar. In the actual system, the channel estimation algorithm would use the OFDM preamble or the pilot symbols to derive the channel estimation. So the equalization happens in the frequency domain so that we need to transform the channel impulse response using the FFT function. So equalization happens in the frequency and it transforms channel impulse response using the FFT. So MP channel set the FFT size by passing the second input, that is number of carriers. Number of carriers, agree? Why number of carriers? Because we are dealing with that FFT size only with respect to OFDM demod also, right? OFDM mod also we are having number of subcarriers as the output, where FFT size is nothing but number of carrier. So that's why we are first converting the frequency domain into FFT. The FFT function output starts with a zero frequency component, but out of the OFD mod function specify the zero frequency component in the middle of the frequency range. So use FFT shift to shift the channel spectrum so the zero frequency component is in the center. So that's why we first will do a FFT shift. So it shouldn't start with zero frequency component. That's why we are doing FFT shift to move it to the center. Task transform the multi-path channel impulse response to the frequency domain. So we will do here. First of all, we have to shift to the center is equals to FFT shift FFT feature. So this is what the frequency domain representation, and zero is kept in the inside. So we can also see using scatter plot, no scatter plot nine step. So if we want apps, oh, I think zero frequency converters anyways should be shifted to the middle. Now you are ready to equalize a signal. So as we know, that will be element wise. So what will be the output and input? So OFDMD mod divided by, so equalization output is. But here the channel estimation we're not employing the channel estimation techniques. We are already having impulse response of channel, multi-part channel, but in practice we don't have. So where we deploy channel estimation techniques. So scatter plot also we need to create. So scatter plot equal out. So here at least after equalization it is looking far better than the previous one. So at least symbols we can separate it out. So the scatter plots of the equalized signal much more closely resemble the desired constellation. The constellation equalization has removed much of the multi-path channel effects. So this was the multi-path channel effects you can see here before equalization. The and equalization has removed much of the multi-part channel effects. The script demodulates the QAM 16 QAM signal and calculates the bit error. The frequency domain equalization greatly improves the link performance even in the presence of multi-part channel. To see the effect of equalizer on just multi-part channel, try increasing the SNR to 100 or line 5. So line 5, 100 if we can see 100. So in this simulation, every subcarrier is a data subcarrier, but this isn't always the case. Some subcarriers are designated for other uses. So you can see everyone is properly separated. So SNR also plays a very important role here. So every subcarrier is a data subcarrier, but this isn't always the case. Some subcarriers are designated for other uses beside the data. In next carrier, we will see subcarriers, some null subcarriers. Okay. Yeah. So OFDM systems are often designed with additional characteristics beyond cyclic prefix. Okay. For instance, they often have the guard bands, a set of unused subcarriers at the low and the high portion of the allocated bandwidth to minimize the interference with the adjacent signals. So we also have some guard bands and also null subcarrier. They're also often zero on the subcarrier at the DC, so that the analog electronics can perform can operate on a signal without a DC component. Practical standards-based OFDM signals often include pilot signals to add in channel estimation to help in channel estimation and equalization. Okay, so you can implement all these design capabilities with the OFDM mod function. In this activity, you will consider only card band and DC specification. So these subcarriers are called null subcarriers because they do not transmit any data. Okay, so what I mean to say is, so OFDM symbols are act systems are often designed with additional characteristics beyond a cyclic preference. So there are some subcarriers that doesn't perform anything. So they may act as a guard band. They may dull the DC. So basically we have some unused subcarriers at the low and the high portion of the allocated bandwidth that will minimize with the adjacent signals. The interference, because if we don't have some subcarriers at the transmitter and the receiver, it will have the interference, okay, with the adjacent signals. We also often zero out the subcurrent DC so that the analog electronics can operate on the signal without a DC component also. So thus there's some null DC component. Okay. So let's see some null subcarriers. These subcarriers are also called null subcarrier because they do not transmit any data. So in this activity, we will have to consider only card bands and null DC specification. In MATLAB, you identify there are some 7 tasks. So in MATLAB, you identify a subcarrier by its index. The subcarriers are numbered from left to right, starting from 1 and ending with number of carrier. The OMD mod and OMD mod and OMD mod functions order the subcarriers on the most negative frequencies to more positive frequencies, with a zero frequency component in the middle. Okay, so as we know how we calculated or how we obtained the center frequency, that was through that was through that was through what? FFT shift, right? Yeah. So with the zero frequency components in the middle. So to specify the guard band indices, first set the number of subcarriers in each guard band. Okay. Then you can define the guard band indices using the colon operator. The operator guard band indices are defined as 1 to number of guard band carrier. Similarly, you can define the right guard band indices from number of carrier minus to number of guard band to number of carrier. So I think this you can understand. Number of carrier minus number of carbon carrier plus 1. Number of carrier. So define the carbon size as number of carrier divided by 16 and so the number of carbon carrier. Number of carrier was 1881 something, right? So define the left and the right carbon. So this 1, 2, is equals to plus 1 to number of carrier. The OFT mod function specifies a zero frequency component in the middle of the frequency range, and this means that DC null subcarries a center index. So we can define when there's a even number, the DC null index will be simply this one. So as it was always even number. So to create a column vector of the null subcarrier indices, concatenate the left card band DC null and the right card band, then the transpose. So let's have some column vector. First, let's have this DC null one is equals to number of carrier plus 1 divided by 2, right? Divide by 2 plus 1. How come? Because it is going for number of GB carriers. If it is only 0, like MATLAB, since MATLAB starts with 1, that's why we are adding 1 here. Is equals to GB left DCIDX GB right. And then it is a transpose. Okay. Now, the total number of subcarriers is number of carrier. Now, however, all the subcarriers are not a data carriers. The simulation sends 16 com symbol per data subcarrier, which means the length of the source bit sequence based on the number of data subcarriers. To determine the number of data subcarriers, subtract the number of null subcarriers from the total number of subcarriers. So the number of source bits to generate is then the number of data subcarriers multiplied by the bits per 16 com. So let's have first calculate the number of data subcarriers stored in the variable number data char, then divide and do that. Is equals to char minus length of null index. Right. Number of bits nothing but let's see whether this is correct or not. Yeah, it is correct. We can see solution also. Maybe they have done different way. Task 3. Same way, same thing. Okay, so task 4. After setting the number of source bits, the script creates a source bit sequence and modulates using 16 com. Okay, that is source bits, number of bits it is creating, and then it is modulating, and then it is doing the demodulation. Sorry, it is com modulation. Source bit modulation order input by Okay, after COM modulation, you will do the IFT or OFDM mod, right? So now you can use the OFDM mod function to perform the OFDM modulation to specify the null subcarriers. Pass the index vector as fourth output, null index. So perform the OFDM. So we have first OFDM out is equals to let's first copy this one only. So signal was this one. Okay. Number of carrier was num_char in our case. I can put directly as 32 here. I don't know what is this. 32. So correct only. So next the OFDM modulation is sent over the channel. So channel is done here. So when this modulation exists, the code runs. When you complete, so this is exists. Okay. So variable it exists. Then MP channel is equals to filter. It will filter using MP chan. One is again in OFDM mod out. Take it till filter out. So just a multiplication it will do. Okay. Then chan out is equals to AWGN and P chan out SNR measured. Okay. Then we have to perform OFDM demodulation. So to perform the OFDM demodulation on the received signal using OFDM demod, because there are null subcarriers were used, the function needs two additional inputs. The symbol first one is symbol sampling offset and the null index vector. So here you have some doubt on why we are using sampling offset, symbol sampling offset. Why we are using this? The symbol sampling offset is a number of signal samples to discard before performing to IIFT. It can be any value. So symbol sampling refers to the number of signal samples to discard before performing to IIFT. Okay. So it can be any value from 0 to the cyclic prefix length. Okay. So to remove the information corrupted by multipart channel, it should be larger than the length of the multipart channel impulse response. So again, the length of the channel impulse response was 17. Then later, we had cyclic prefix length as 32. Then sampling simple offset, which can be anything, right? Let's say we have to perform an OFDM demodulation of the received signal churn out, specify the number of carriers, number of cyclic prefix length, and also for the sampling offset length, use the cyclic prefix length only. That's fine. So OFDM demod out. Churn out. Num carrier. What are the inputs? CP length. CP length. Again, we are providing that as a CP length only. Symbol offset. Okay, then I'll so while doing over modulation, we didn't provide this simple offset, but yeah, uh, we only provided this cyclic prefix length and all. We didn't provided symbol offset. The CP length, okay. CP length, I have defined some other cyclic prefix length. Okay. I can just provide 32 else. Not many students are there. Some error is there. Let's see the solution. Or the okay, this is not capital, this small. But while doing modulation also it was small. Okay. So next step is to equalize the signal. Transform this again we can do the transform shift the channel impulse response because again we want to have zero at the middle. The channel frequency response has a number of carriers as a frequency components. However, the OFDM demodulator output only contains the data carrier subcarriers. Okay, to perform the element wide division, you need to remove the null subcarrier frequency count for the channel frequency data subcarriers. So you can remove the specific elements of vector using indexing. That's great. So transform the multipath channel impulse response to the frequency domain and shift it to that one. We can is FFT shift FFT MP chat num yeah. Okay. Then MP change frequency. Remove the elements that correspond to null subcarrier. So you can remove the elements of a vector. So we need to remove this one, right? Null subcarrier. So null index. I hope this is correct. Frequency and pitch and frequency and pitch and number carrier. FFT shift. FFT number of carrier. Num carrier. What was there? Num carrier. Let's see the solution. What is this? Task 6. I think we have done the same. FFT shift, FFT, MPG number carrier. Null index. I don't know what we have done wrong. Let's remove it and do the next. So equalize the signal by dividing M pitch and frequency, name equalize out. So let's do that. Equalize out equals to OFDM. So remember few things, right? First of all, we are removing some null subcarriers. We had the idea of removing that also. So understand like how we are doing it. So I don't know what is this. Okay, we have to create the scatter plot as well. So scatter, let's not have this. Scatter equal out. Oh, let's see the solution. Oh, scatter plot. Yeah, so congratulations, you have simulated a practical OFDM symbols with card bands, null DC, and frequency domain equalizer. You can visualize the spectra of transmitted and noisy same signal by uncommenting the code. So we can visualize also. Oh, so, so the transmitted OFDM symbol is yellow. That's great. And the noisy multipassing is blue. You can see the guard bands and there is frequency selective for fading on the multipath perspective. So received is blue. Guardman is like this side and multipath fade, selective fading. That's correct. Okay. So there are few sections, I think. Now in a way to doing real or practical communication system using MATLAB. So you would like to learn the techniques, check out the Get Started toolbox with the communication, generate and analyze signals, apply impairments, correction, model channels, propagation effects, perform link level simulation, apply artificial intelligence techniques. So you can download the wireless communication on web course on the help menu, course files. These files include the sample simulations for the functions of the course. So it's excellent, excellent. Okay. So this was a one of the math work training, but yeah, we also saw the basics of MATLAB also. We covered everything here, logical arrays, programming, documentation. Now I would like to share you something regarding the questions previous week. I don't know why it is not good. So given a random process xt, so as we know what is random process, let's open with just download. So given a random process xt with a power spectral density xSSF. So what is power spectral density? It is the Fourier transform of the autocorrelation function, and the autocorrelation function is nothing but the expected value of x with xt minus tau, xt with xt minus tau. And if you do the Fourier transform, you will get that autocorrelation, spectral density, power spectral density. And if you find the area under the power spectral density, that will be the power. And when it is passed through a LTI system, there's another random process yt whose power spectral density is given by, we know this as answer. It was xt, sorry, LTI system. This is with HF. That will be HF square into XSF. Why? Because this is, first of all, in time domain it is a convolution. If you do it in the frequency domain, it is multiplication. And if you do square, because power is square of x square t. So this is the answer. Because when a wide sense stationary random process with a power spectral density xSFF pass through a linear time invariant system with impulse response, the output is this one. And the power spectral density of yt can be calculated with Fourier transform. Mathematically, it is written like this: PSD. Okay, there's a frequency response, and a random process xt is called white when power spectral density is flat, the correlation function is flat in time, the autocorrelation function is flat in lag, the power spectral density is an impulse function. What do you think? Nothing but the power spectral density is flat. That's why for AWG channel we consider and not by 2 PSD for noise. Because a random process is considered white when its power spectral density is flat. This means the power spectral density is constant and equal to the finite value at all frequencies. In other words, the energy of the random process is uniformly distributed across all frequencies. This is often represented by the flat horizontal line in the frequency domain, indicating there is no preference for the specific component. Option 1 clearly defines. If a random process xn generated using linear combination with sparse values in innovation component, that is known as, anyone? Mahima, Disha? Yeah, so sir taught in the class that is auto-regressive process. We will simulate this also in MATLAB. Because it is, if a random process can be generated using linear combination with sparse value in the innovation component, this is called autoregressive process. The autoregressive process is the type of random process in which the current value of the process is a linear combination with sparse value along with the stochastic or innovation component. So that's why the C is equals to pi 1 multiplication of xn minus 1 plus pi 2 xn minus 2 plus phi p xn minus 1 plus zeta. So these are the current value, these are the past values, and these are the coefficients or the autoregressive terms which determine the linear regression and this innovation component. So zeta n, which is function of time, is a innovation component. So innovation component which represents the stochastic or a random part of the process. Since AR process, autoregressive process are commonly used in time series analysis and modeling to describe the dependence of random process on its own peak value. So this order P specify how many past values you have to consider. Okay, so a moving average random process can be generated by passing a white noise through an all zero filter. That's correct only. Why all zero filter? Why? Because it is a white noise process. White noise process is a stochastic process where each sample is a random variable with constant mean and all. The samples will be uncorrelated, no autocorrelation. So it is often represented by zeta t. So given a xn is a first order autoregressive process, then this will be, so let's solve this, e of x of n, e of x of n minus 1. This is what? This is what? Auto. PSD is a Fourier transform of? PSD is a Fourier transform of? Nobody's responding. So this is P, and if it is this one, so first order AR process is represented as xn is equals to alpha xn minus 1 plus wn. So in that case, n minus tau, this p power tau. Answer is p power tau. So explanation is given here. You can represent here. So in Markov chain with state transition probability transition matrix P, the state J is excible from the state A when 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 Pn ij not equal to 0. Definitely, right? Then only it will be excible to from state J to N. And Markov chain is a discrete value random process where the probability of the process being in the state n depends on the time index n because it is asking from the index n plus 1. It only depends on the previous one. Huh. Correct only. So yeah. So you have got all the questions. Given an xn is a first order autoregressive process such that this one is autocorrelation and this one is the rho, then the variance of the inversion component can be calculated. We can calculate using this formula E of xn S star sigma. Okay, we are already running out of time, so this is P by sigma because this is variance is this one autoregressive. So I hope we have covered almost all the sections. We will see this autoregressive in the next class. And thank you so much for joining. Mahima Nishant. So I'm leaving today's class.